All right. I think this is called an Atwood machine or Atwood's machine. I'm not sure. And maybe it's not the thing, but it's similar. This is a frictionless pulley, frictionless massless pulley, and these two masses are hanging from it, and there's no air resistance, and the strings are massless. It's a perfect physicsy problem. So we have to find the tension in the string and the acceleration of each mass. For these kinds of problems, you have to analyze different systems, and analyzing various systems will allow you to find various things. And generally, to find an acceleration, you'll need to analyze the entire system, and then to find tensions, you'll need to analyze particular parts of the system. Because the tensions within here, for example, the tension pulling this block up and the tension pulling that block up, they're part of the same string, so they're equal, and they're pulling opposite one another, so they cancel out, so you can't really solve for them if you add up all the forces for this system. So you'll need to, we'll do the whole system to get acceleration, and then we'll do part of the system to get the tensions. Break. First thing I did was drew my diagram, like always, and I've added in some extra things that you wouldn't know when you're first drawing your diagram. But I made a decision just for consistency. I needed to decide which way was going to be my positive direction. And it's tricky because usually up is positive, but as one block goes up, the other block goes down, and I'm just calling this sort of motion positive. So if this goes up, I'm considering that positive. If this goes down, I'm considering that positive for my beginning analysis. And my beginning analysis, can't really tell what order I did this in, but it was analyzing the 10 kilogram system, the entire system. So I drew my blocks, I drew my weights, and those are just mass times gravity, 3 times 9.8, 7 times 9.8. And then I drew in tension. I didn't know this was 41.2 or that was 41.2. I just had a T. And I do know they're equal because tensions are equal in the same string. So this is net force, and this is net force. This is net force with F equals MA. Don't know A yet. I'm looking for it. And this is net force as the sum of the forces. So there are really just two forces acting on this system. There's the 29.4 Newton force, which is the weight of this block, pulling positively. And there's a 68.6 Newton force, which is the weight of that block, which is pulling what I'm calling negatively. So if I add up those forces, I get negative 38.9, which tells me overall this is moving counterclockwise. So that net force equals 10 times A. Here's my equation. And so when I solve for A, I get negative 3.92. And here I'm just trying to be really clear about what that negative means. It means the whole thing's moving counterclockwise. So 3 kilogram block is moving up, 7 kilogram block's moving down. That's exactly what you would expect with a heavy block and a light block. So in the second part, this is where I find the tensions. This tension and that tension, they're the same. So I arbitrarily decided I would just focus on this block. Doesn't matter. It'd be just as easy if I had done that one. So instead of a system with a mass of 10 kilograms, which would be the entire system, now I'm just looking at this block, and I'm adding up all the forces acting on that block, and I'm multiplying that block's mass times A. So net force is this tension minus this weight. T minus 29.4. I guess I should point out that now, looking at this, it makes a lot of sense to me to call this a positive force and this a negative force, even though before I was calling this way positive. But now I'm saying T is positive, this weight's negative, and then the other way to write net force is mass, 3 kilograms, times acceleration, 3.92. Now this is a positive number because the whole thing's accelerating counterclockwise, so this is going up. So that needs to be positive. If I had done the 7 kilogram block, that would be the same number, but it would be negative because it's going down just as fast as this is going up. So 3 times that is this. That's the net force. Set it equal to that. And T comes out to 41.2 newtons. And by the way, you might think, well, if this is 41.2, then that's negative 41.2, but for tensions, just use a positive number. We could talk about why later. Number 9. Oh, kind of typical when you see one of these, if there are 3 forces like this, and some friction, even if there's not friction, you're going to have to analyze 3 different systems, draw a bunch of forces. So here's my diagram to start with. Each of these blocks has weight, so you draw the weight on all of them. This one will have a normal force acting on it because it's on a surface. These 2 will have tensions acting on them because they've got strings. This will also have tensions. So this one has 1, 2, 3, 4 forces, but one more force because as this heavy block goes down and this light block goes up, this is going to slide to our left, and that's going to create friction to the right. So I've got to draw as many of those forces as I can and write their values, and then I can analyze the 3 different systems. So the weights are all just mass times 9.8 is this. Mass times 9.8 is that. Mass times 9.8 is that. This weight equals this normal force. The tensions, I didn't know these in the beginning, so you can't write them down at first, but I just called this T2 and T1 to designate the 2 different strings. And then I thought about, well, which way is the friction going to act on this? This is heavier than that, so it's all going to go like this. If this block slides to the left, friction is going to act to the right. I could calculate the force of friction using mu times the normal force. Mu was given as 0.2. The normal force is just the same as weight. So mu times that is 7.84. So this has got a force of friction of 7.84 to the right. So now we've got to find the acceleration of the whole system and the tensions in the 2 ropes. So first, use the entire system to find the acceleration. If you use the entire system, then all these tensions are internal and canceling, so we don't have to include any of them when we add up the individual forces. The entire system is 3 plus 4 plus 5, which is 12 kilograms. So the net force on it is 12 times A. And the net force we can also arrive at by adding up all the non-canceling forces. Got to decide what's going to be positive and what's going to be negative because we've got the situation of something rising while something is sinking. I decided my convention is going to be clockwise is positive. So here's a force that doesn't cancel. Here's another one. Here's another one. And that's it. So this force is downward, which is positive. It's part of this clockwise direction, so it's positive. This is to the right, clockwise, so it's positive. This is to the left, counterclockwise, so it's negative. So of those 3 forces, 49, 29, 7.84, the only one that's negative is 49 because it is opposite the direction that I designated as being positive. So the net force is negative 11.76, which means net force counterclockwise. So I can set 12 times A equal to negative 11.76 and then solve for A. I get negative 0.98. And here I am being really clear about what this negative means. It means counterclockwise, which means this goes up at 0.98 meters per second squared, this goes left, and this goes down at 0.98 meters per second squared. Now to find the tensions in these 2 ropes, I need to separate out and analyze an individual system that only includes one of these t's. So I could just analyze, I can't start with this because that would give me a couple of unknowns. I wouldn't know this t. So I could, I guess, analyze this system, because it would just be affected by this one t. But it's a lot easier to pick one of these weights on the end. So I think I did this one first. So for the 5 kilogram system, the mass is 5 kilograms, the acceleration is negative 0.98, and it's because everything moves counterclockwise, so this is going down with an acceleration of 0.98. That's why this is negative. And so this is F equals ma. I get negative 4.9. The other way to write the net force acting on this, there are two forces. There's T1, which is positive, and weight, which is negative. So T1 minus 49 equals negative 4.9, and that gives me T1 equals 44.1. Now, if I want to find the tension in this rope, again, I could now analyze this block because I know this tension. I know everything. I'd be able to just solve for this, but there are more forces acting on that. Who wants to bother with more forces? This is a lot easier. So with this, the net force is going to be 3 kilograms using F equals ma, 3 kilograms times positive 0.98. It was negative 0.98 here, but now it's positive 0.98 because this is moving up, whereas that was moving down. And I'm going to just say up is positive now. So up is positive means positive acceleration. It also means T2 is positive, and it means this weight is negative. So I can write out T2 minus 29.4, that's the net force, this minus this, equals mass times acceleration, which is that. So I'll set this equal to that and get 32.3. And when you're done, it's not a bad idea to go back and see if things make sense. Put these numbers in and then say, okay, so this block has a tension of 32.2 newtons pulling it up and a weight of 29.4 newtons pulling it down. That means it's going to accelerate upward, which is what it does because we've got counterclockwise acceleration. And over here, this has a weight of 49 newtons and the tension is only 44.1, so this is going to be accelerating downward. That all makes sense. So you could go back and check things, and that should equal, if you do this number minus this number, that should equal 5 times negative 0.98